few minutes to review some of the rules of probability from Lesson 3, as well as pay close attention to some of those concepts as it related to the homeworks. So first, let's consider the situation where we have two events, A and B, and recall that this is called the intersection, the point where they overlap, and that is denoted like this, A and B, and again, that's corresponding to the word and. So, in situations where we want to observe both events happening, that's denoted by this intersection of A and B, as in both instances are occurring. Now, if we were going to look at both circles, this is the event A or B. And so this is the case where either A is happening or B is happening. And so that's both circles filled. And this is also called the union of A and B. From this drawing, we can kind of derive the probability of A or B happening. So the probability of this union, well, we have A is happening, so we want to take into account that probability. Or B could happen, so we want to take into account that probability. However, you notice that when we do this, here's the probability of A, here's the probability of B. You'll notice that we are counting this middle section twice. We don't want to count that twice. We only want to count that once. So we have to subtract out the probability that we're in that intersection. So we subtract out the probability of A and B. So now we have a formula for finding the probability of a union. Now, a mistake a lot of you made, and it's understandable, is that we forgot this last little piece. But this is very important because if we neglect to count for that, we are going to be double counting it and could possibly go above 1. But remember, in probability of any event A has to be between 0 and 1. So be very careful. If you ever get a probability that's not between 0 and 1, you may want to recheck your work. Now, there are some cases when you can, now let's say in this situation, notice there's no overlap here, and this is what we call disjoint events, or mutually exclusive. So when this is the case, the probability of A and B becomes 0. So then we are left with just the probability of A union B equals probability of A plus the probability of B without that extra piece. However, in general, you should always subtract out your probability of A intersects B when you're looking for the union. But if they are mutually exclusive, that probability will end up being 0 anyway. But it's always a good practice, so please be careful when you're trying to calculate that union that you're subtracting out their intersection as well. And then let's quickly go over what a complement is. So if this is my event A and the rest of this square represents the rest of the sample space, A complement because it becomes everything in that square. So essentially A complement is everything not in A. It's also denoted as a little A prime, A complement, that little dash there also means A complement. So if we wanted to find the probability of A complement, well, since probability always sums to 1, this is simply 1 minus the probability of A, and vice versa. Probability of A is 1 minus the probability of A complement. So when would I use this? Well, sometimes it's far easier to find one event versus the other. So you may want to use this relationship in those instances. So let's look at conditional probability. Or first, let me go through one more example on how we can use this formula here. So, or rather this whole formula. So in general, even though this formula is for the probability of A or B, mathematically we can rewrite this if we move the probability of A and B to the other side to get the probability of A and B. And you're going to see it's a very similar formula. Probability of A plus the probability of B minus the probability of, in this case, A or B. So all we did was move the intersection to the left side, the union to the right side, and we get this formula here. So now we have another formula for probability of A and B from that same formula. So again, this was another formula that possibly may have been helpful in the homework or may be helpful in other problems as you move forward. Okay, so now let's look at conditional probabilities. So conditional probabilities are defined to be A given B. So in this case, this is the condition. So this is my known information or my given information. So whatever situation we know to be true, that goes after the vertical line. And then the event before the vertical line is the probability we're trying to find. And we find this by finding the probability that you're in A and B, so the intersection, so that the place where those circles overlap, divided by your probability of your given information. So the one that goes after the vertical line goes on the bottom here. And that's because what we're really doing is shrinking our sample space. So instead of looking at the entire sample space now, we're simply looking at the sample space that contains B. So that becomes my denominator, because remember, when you're finding probabilities, the denominator should represent the whole sample space. But in this case, our sample space is simply B. So the probability of B goes on the bottom. And at the top, we now, instead of just using probability of A now, we must use probability of A and B because we shrunk in our sample space and have to take that into account. So this is the general definition of conditional probability. And notice that if we rewrite this then, now we find that probability of A and B, if we multiply probability of A on both sides, gives us the probability of A given B times the probability of B. So now again we found another formula for A and B. And so before we used the formula by rewriting the union definition, and now we can find a formula by rewriting the conditional definition. So anytime you're given a conditional probability, this should be the formula you are using. Okay. And finally, and we're going to go over independence. This is a very big topic and a very important topic of probability. For A and B that are independent, so if A and B are independent, the following is true. The probability of A and B, or A intersect B, is their product, probability of A times the probability of B. You may have seen this book as the multiplication rule, but be careful. This is only when they're independent. Some of you are using this formula on your homework in other situations. But in those situations, you should have either used this formula, or if we go back to beginning, this formula that was derived. So we have a couple formulas for A and B, but when they're independent, it's a different formula. So please be very careful. And the other thing I want to note, that if I ask, or on a test or a quiz lab, my stat lab, if they're asking, are these independent, we're asking you to check this fact. Not to provide, based on the scenario, if you think they would be independent. We want you to check this mathematically using this formula. Because sometimes things seem like they should be independent and they're not. And so the best way to really do it is just to check this formula and then afterwards think about, does this result make sense in this context? But you should be using this formula. And there is an alternative formula for independence. If we go back and look at this conditional formula here, the conditional formula, and again, the conditional formula holds for all cases, not independence, but this is the conditional formula. But we just found out that when A and B are independent, I can replace A intersect B with this product. So if I do that on top, replace the numerator, what happens? We have two numbers here. And in mathematics and algebra, when you're dividing one number by the other, you can cancel them out. So we find that the probability of A given B equals probability of A when they're independent. Again, only when they are independent. So here is another way you can check independence. So we can check it either by checking that the intersection is equal to the product, or that the given information is equal to the probability without the given information.